Alright, so our last portion of Chapter 5 is I thought we would practice a little bit with some trig ones where our other strategies are going to involve the use of identities. So I thought that since, we always have a weakness in our trig substitutions, that we would take a look at a few of these just to kind of see where sometimes we might use a trig substitution. Now, in this one, we've seen something similar to this before. It actually is an example where we have a product and where one of the factors is a derivative of the other. So I would probably simply do this one by letting u equal sine of x. So my du, derivative of sine, is cosine of x dx. So when I integrate this, I'm essentially going to put my box, okay, again going back to the box analogy, that I have a box which is the u is sine of x, and then this is the stuff that gets packed back into the box, so that's my du. So I'm really integrating u du, which is a power rule problem, so we end up with the antiderivative of u, which would be 1/2 u squared sine of x squared plus c, or 1/2 sine squared of x plus c. So that was a standard 5.5 section power rule problem. Then we see something like this, and again, still going to be a standard power rule problem. I might rewrite this as sine of x squared cosine of x dx to kind of reveal that I'm going to let my u equal sine of x here. My du is my cosine of x dx. So my box in this problem is the sine of x squared, or u squared, so that's what I'm integrating. So it's the integration of u squared du, which would be u cubed 1/3 plus c, or 1/3 sine cubed of x plus c. So those are fairly straightforward, what you were used to seeing in section 5.5. Now when I take a look at this, what kind of bothers you there is the fact that you have this sine squared, and the problem is that I don't really have a derivative here. So I'm going to have to do some work with this one and maybe some trig identities to help me out. Now you might be tempted, when you look at this, to let u equal sine of x like I did here, but the problem is I don't have a cosine in order to get the du in there, and so I have a problem that I can't do that u substitution. The second thing that students typically try to do here is to go, well, I know that sine squared x plus cosine squared x is equal to 1, so they're going to say, all right, well, I can take out sine squared x and put 1 minus cosine squared x in. But this is still a problem because all I did was switch from having sine to having a cosine. I still do not have the derivative I need if I were to make a u substitution. So that doesn't help me either. The trick to this one is to remember that we have identities called the power reducing identities. And the power reducing identity for sine squared of x is 1 minus cosine of 2x all over 2. That's one of the power reducing identities that you should know from your trig class in prior years. And so what we can do is use this identity and change this to, instead of integrating sine squared, I integrate 1 minus cosine of 2x over 2 dx, which is essentially the same as integrating 1 minus 2, or 1/2 minus, I'm going to bring the 1/2 out, the integration of cosine of 2x dx, and don't forget your dx on that one. So I can integrate a constant, 1/2 x, and then here I'm going to have to do a u substitution. I'm going to let u equal 2x, du equals 2 dx, so I'm missing the constant, so I put in a 2 and I take it out. So I actually end up with, in terms of my antiderivative, oops, that's the subtraction, so minus 1/4, and this ends up being cosine of u du, And the antiderivative of cosine is sine of u plus c. And so I can use an identity, and the problem is that having this power means that if I try to do a u substitution, I need the derivative of sine somewhere, and I didn't have it. So I use a power-reducing identity in order to calculate this. All right, now let's take a look at this. Again, the same problem is going to arise. I can't let u equal sine of x because I don't have its derivative cosine anywhere in the problem. The trick to this one is to recognize that I can split this to sine squared x sine of x dx, and that what I'm going to do now is I am going to power reduce over on this one. I don't know why that's starting to get a little weird. Whoops, redo. All right, so let's take a look at this, and let's now power reduce this one. So I'm now integrating 1 minus cosine of 2x over 2 times sine of x dx. Oops, not quite enough room. I'm going to come right down here so I have a little bit more room. That's the same as, now I'm going to distribute the sine through, and so I'm going to have sine of x over 2 dx minus cosine of 2x sine of x dx. Whoops, sorry. And that's what we're going to take a look at. Now I'm going to evaluate this, and then I'm going to realize at this point that using the power reducing identity here actually created a problem. This I can integrate, but this, because it's cosine of 2x, the derivative of cosine is sine, yes, but the problem is that that has an x and this has a 2x. So that method actually fails here. And so then I go, all right, I must not be able to do this method. Is there another identity where I can substitute for sine squared? And the answer is yes. In this case, and this is kind of what can confuse you, remember I said that integration, it's a little bit of guess and check. You think about the different things you can do, you try them, and then you recognize if it doesn't work, you back up and try the other one. So like here, I tried the 1 minus cosine squared, and it didn't work, so I went to a power reducing. Here, I tried the power reducing first, and that's not going to work, so then I said, all right, well, let's go to the actual Pythagorean identity. All right, so ignoring this step then, so now we're going to come down and we're going to use the Pythagorean. Now, in using the Pythagorean, it would become 1 minus cosine squared x times sine of x dx, which would then, after distribution, become the integral of sine of x dx minus the integral of cosine squared x sine of x dx. And then we cheer a little bit because this is actually working. The antiderivative of sine is negative cosine of x. And then over here, I can do a u substitution. That I can think of this as cosine of x squared, so I can let u equal cosine of x du. The derivative of cosine is negative sine, so I have that out here. I need a negative, so I add that in. I like to always add that in red, although I'm in red, so add a negative and take a negative out. And then so this part will be du, and so now I'm integrating the integral of u squared du. And then we integrate this, so we end up with our u, cosine of x cubed, divided by 3, 1/3, plus c. And so that shows you a couple of examples of using your trig identities. Look for Pythagorean, look for a power reducing identity in order to attempt to make the integration. All right, now a nice easy one for you to look at. When you get to this, it gets to the point where you're so used to seeing really complex ones, sometimes you forget the easier ones. This is a u substitution. U would equal 2x minus 1. My du would be 2 dx. So I see that I am missing a constant because I only have a dx here. So I'm going to add the 2 in and take the 2 out. And then what I'm going to end up with is going to be 1/2 the integral of u to the 1/2, that's the square root of u, and then the 2 dx becomes du. And my integral is 1/2, add 1 to my power, u to the 3/2, divide by my power, which would be multiplied by 2/3, plus c, and then switch back to the correct variable, 1/3 2x minus 1 to the 3/2 plus c. All right, so that's fairly straightforward. We kind of throw it in here because you get a little confused after we've been doing inverse trig and the fractions and all the log rules. And so you see a simple one like that and you're like, oh my God, I have no idea what to do. All right, now our last kind of technique down here is, a lot of times I do the u substitution as a setup, but I don't actually substitute. Sometimes I do the u substitution and I show the u being plugged in because it's a little easier to integrate, to see what you're actually integrating by putting the u in. But there are times where you're kind of stuck doing a u substitution, that the u substitution itself is necessary to turn something from a form you can't integrate into something that's a form that you can. Now let's take a look at this example. The problem you have here is you might be tempted to try to head toward an inverse trig, but that's not the difference of perfect squares. There's not a fraction. So we're like, well, what do I do with this? You're like, well, if I'm in the u substitution section, maybe I should do u equal to 2x minus 1, but then du would be equal to 2 dx, and the problem is we don't have a derivative out here. But, well, here's our trick. If u is equal to 2x minus 1, okay, if this, then I can also get a formula for x as well. So x, solving this equation right here for x, if I take u, I add 1 to it, and then I divide by 2, I actually have a formula for x in terms of u. And so sometimes, if it doesn't work by doing a u substitution like our normal way and we have the derivative on the outside, what we can do is convert this so it's all in u. I'm going to take this x out, put in u plus 1 over 2, my square root, and then I'm going to make my 2x minus 1 u. So I turn this into a problem, and then notice that I need to fix my dx. I'm missing the 2 dx part. So I need to add in a 2 for the 2 dx and take it out. So that's going to leave a 1/2 out here. And so that way I can take out the 2 dx and put in du. Now, so I've changed everything, and you might be like, well, what good did that do me? I still have something that I don't really know how to integrate. What that did for me, though, is take a look at what we have. I'm going to pull this 2 out and just pull the constant out, make it a little easier. This is 1/4. And then I have u plus 1 times u to the 1/2 du. Now take a moment and look at this. This I was having trouble integrating because I can't distribute something outside of a square root in. But notice by transforming everything into u, I've turned it into something that, oh, wait a minute, I can distribute this. I can turn this into basically power rule integration. So it becomes u to the 3/2 plus u to the 1/2 du, and it's nothing more than integrating using the power rule. If I used my power rule, I'd have 1/4, do your parentheses, add 1, which would give me 5/2, divide 2/5, plus add 1, 3/2, divide 2/3, and then of course plus c, and then at the very end you always have to go back to the variable that you started with. So my 1/4 of 2/5, I'm just going to go ahead and distribute while I'm here, would give me 1/10. My u was 2x minus 1 to the 5/2 plus distribute I get 1/6 2x minus 1 to the 3/2 plus c. So I actually, by doing a u substitution a little differently than what we did before, can turn a problem that I can't integrate into something that I can use a power rule on, and then I can integrate it. All right, let's take a look at this one again. Again, we have the same kind of problem we have over here, which is you would like to say, oh, this looks sort of like an inverse sine. But the problem is this is not the difference of perfect squares here. And then you go, all right, well, let's try to use a power rule substitution. So I try to let u equal 2x minus 1, and the problem is that my du is not in the top. I have a higher power up here that's kind of messing me up. So then I'm like, well, what do I do now? I'm going to utilize the fact that let's see if I change everything to u's, and in terms of u, then I'm going to be able to do this substitution. So likewise before, if u is equal to this, then the x is going to be u plus 1 over 2, and since I'm looking at x squared up here, x squared is going to be u plus 1 squared over 4. So I kind of convert everything. Be careful of your corrections. I need a 2 to go with the dx. So I put in my 2, I take out my 2. We're going to change this to be completely in terms of u. So the 2 dx is going to become du. The x squared is going to become u plus 1 squared over 4. And this is going to become u to the 1/2 down here in the bottom. And again, taking a look at it, how did this help me? I'm going to bring the u to the 1/2 up. I'm going to pull the 4 out. Let's make this an 8. And then I have u plus 1 squared du. Now, take a look at that. Why is that something that I can integrate? It's not actually going to be another substitution. It's, I can multiply this out. I can distribute the u to the negative 1/2 through, and I'm going to end up with a power rule integration. So let's go ahead and do this. This would give me u squared. Let's go ahead and just do it in 2 steps. U squared plus 2u plus 1 du, which is going to be my 1/8. Now I'm going to distribute, and remember you add your exponents. So I'm going to have u to the 3/2 plus 2u to the 1/2 plus u to the negative 1/2 du. And now I can integrate because it's all power rule problems. So by doing this change of variable from x's to completely in u's, it does still help me. It has this additional step that I have to solve for some x's, but it will help me. So I get 1/8 u to the 5/2 2/5 plus u to the 3/2, divide by 3/2, so that's 2/3 4/3, plus u to the 1/2, divide by 1/2 2, plus c, and then at the very end change yourself back over to your x's. So we would end up with 1 over 20, my u was 2x minus 1 to the 5/2, plus 1/6, I'm distributing my 1/8 as I go, 2x minus 1 to the 3/2, plus 1/4, 2x minus 1 to the 1/2, plus c. And so there's our integration for that. So this is a technique where sometimes if it doesn't work out nicely, like it is doing for a lot of our prior u substitutions, we in addition go ahead and use our u equation to solve for x, and then substitute out all the extra stuff that's bothering me that's outside of the power rule that I want to use. Okay, so that's kind of a last resort. I would only do that if I have tried everything else and then it's not working, and if it's in this chapter, that means you have to be able to do it. I would then try this technique. All right. I'm going to leave these 3 for you to try on your own, and come back. So I want you to pause the video, Try these 3 problems and then come back and check your answers. All right, so coming back, you're probably going, those were really hard, but let's take a look at them. This one should have been fine. You do the u equal to x plus 1. You realize that you have a slight problem, so you do your du and you solve for x. So here was that using the change everything to in terms of u, that by doing that, I could turn it into something that I could then distribute. And be careful, I could use power rule here, but that was a log rule, and then work myself back. So that was your first one. Should have been difficult, but possible. Now let's take a look at what I did up here for part D. Now what I did first is recognize that I can distribute this square root of x through. And when I did that, I got to here, and then some alarm bells should have been going off to say, oh, wait a minute, we've seen this before. This is a complete the square problem. So I went ahead and completed the square, turned it into the difference of 2 perfect squares, which is my arc sine, and I applied my u over a rule that I had for that. So possible, you just had to recognize that this was actually not a change everything to u problem. This was an algebraic technique where you just had to distribute and then complete the square. Now for the extra challenging problem, let's take a look at this one. Now, and I really need you to understand that even integration itself is an art. It's an art of choosing the correct u substitution to do and to recognize what form you are going to be heading toward when you integrate. It is an art. It takes practice. The ones that are the basic ones, you'll start to, as soon as you see them, you'll know that's a log rule, that's a power rule, that's an inverse trig rule. Some of these other ones, it may take you a couple of tries in choosing a u, and you might go down some dead ends, but you will eventually figure it out. If it doesn't work with your first u substitution, try something else. And I will admit to you, I did this problem initially and I tried to make u equal to 2x, and as I worked through the problem, I realized that it wasn't getting me anywhere. So I backed up, I came back to the beginning, and I changed my u substitution to make it the 2x to the 1/2. Now when I did that, I did my du, and it does end up being pretty complicated, and this is where you went, okay, that's obviously not anything I have there, but notice that dx is really the square root of 2x times du, or u du. So this dx that I had up here in the top, I could take out and replace it with u du. And so I ended up with u du over 1 plus u. And that got me into a form that was an algebraic method of, oh, they have the same degree, so I can use long division. I took the denominator, I divided it into the numerator using my long division. I wrote it in its whole part plus its fractional part. Technically, I should have parentheses here. Then I was able to integrate the constant. And then this was a log rule where I would let my quote-unquote, I have to technically use a different letter, w equal the denominator. Then dw du is basically 1. And so I could do a log substitution and work the problem that way. And so the idea here is the more challenging integrals that you are going to take, it's an art. It's something that you're going to have to just practice and know what options are available to you. What are you looking for? What rules are we looking for? Inverse trig rule, your log rule, and your power rule. You choose a u substitution, and if you have one that doesn't seem to be working, you may look for some algebra techniques to use, completing the square or long division, some trig substitutions to make, and then failing that, if it's in a section that is in Chapter 5, you have to be able to do it. Then we start trying to do a couple of things where we manipulate our u substitution to kind of eliminate all the x's and dx's out of the problem and see if that will work for us. That's kind of a last resort, that if nothing else works, then that's going to be my choice. All right, and then we'll finish out this section just reminding you, I've already talked about this once, that if you are doing an even function and we're doing a definite integral and we're symmetric over 0, your bounds are negative a to a, that if it's an even function, it will always be twice the area from 0 to a. That should be common sense. And if it's an odd function, you should always cheer because you never have to actually do the integration. The integration will always be 0, half above and half below. And so I will leave you to do these examples. Well, let's just do a couple of them real quick. Knowing that this is odd, and then if you look at this, x over x squared plus 1 is odd, that if you see something like this, you go, oh hey, negative 3 to 3, the answer is 0, and I don't have to do anything. Taking a look at this is even, this is even, and cosine is even. So when I integrate this, I can actually change it to twice the integral from 0 to pi of 1 plus x squared plus cosine of x. Now this one's not as nice as the odd ones. However, when you are doing your net change for your definite integrals, it's definitely easier to plug in 0 than it is going to be to plug in negative pi. So that's really the only advantage to this. So we would integrate x plus 1/3 x cubed. The derivative of sine is cosine, so the antiderivative of cosine is sine. Evaluate it 0 to pi. So we end up with 2 times pi, plug in pi, plus pi cubed over 3. Don't forget to distribute your 2. Plus 2 times the sine of pi. Sine of pi is 0, so that's 0. Minus 0 and 0. And sine of 0, which is 0, so we're going to subtract 0. So it makes it just a little bit easier in terms of your substitution, because typically substituting in 0. Slight advantage, not much, a little bit shorter. All right, let's take a look at this. This one we have odd, even, odd, even, odd, even. So I'm going to regroup these, and I'm essentially going to ignore the odd ones because the integral from negative 1 to 1 for the odd is 0. So I'm just going to ignore them and change this to be the integral from negative 1 to 1 of just the evens, x to the 4th plus x squared plus 1. See, it's all about incrementally saving time, which I know is twice the integral from 0 to 1 of x to the 4th plus x squared plus 1 dx, which is going to give me, now I'm going to do my antiderivative, x to the 5th, 1/5, let's do parentheses here, plus x cubed, 1/3, plus x, and we're evaluating it from 0 to 1, and again, that makes it easy. Plugging in 0, your net change, that part will be 0, so we end up with 2/5 plus 2/3 plus 2 minus 0, and we are essentially done. Find a common denominator and add it together. All right, so that will wrap up all of our integration techniques in Chapter 5, and so hopefully you'll be practicing these and preparing for your test.